When a commercial construction company receives a contract to build a 10-story high-rise, they do not begin by pouring concrete. First, the engineering team calculates the exact material requirements, determining how many pallets of bricks and tons of cement to order. From there, they map out the logistics, calculating the total headcount of laborers and projecting the specific months required. None of these calculations are possible without knowing the exact scale. Size is the prerequisite mathematical input for every other estimate. Software development relies on this exact sequence of logic. Before a project manager can predict the capital burn, the development timeline, or the required headcount, they must quantify the dimensions of the software through software size estimation. Building a digital platform requires the same rigorous, sequential planning as physical engineering. The process always starts by defining the boundaries of the build. When determining the size of a digital product, beginners often conflate complexity with the hard drive space it consumes. A standard calculator application might take up 15 megabytes of local storage. A commercial banking application might require that exact same 15 megabytes. However, the banking app manages encrypted user sessions, secure financial transactions, and generates dynamic reports through external databases. Software size is a measurement of functional capacity, architectural complexity, and the raw human effort required to construct the system. Storage footprint reveals nothing about resource allocation. To plan effectively, teams must measure the complexity of the functionality itself. Planning a project involves a rigid sequence of dependencies, where each calculation acts as the baseline for the next. This sequence is mapped through the Stecker framework, which begins with the size of the software. Establishing the absolute size of the codebase allows a manager to accurately project the development window. That timeline translates into effort, measured in continuous person-months of labor. Effort dictates the total cost, as longer project timelines increase the capital required for developer salaries and infrastructure. Finally, those cost and effort metrics determine the specific engineers and hardware allocated as resources. Size, time, effort, cost, resources. We can see this in the planning of a new university management system. The engineering lead determines the system requires approximately 80,000 lines of code. Based on that size, they estimate a 10-month development window, requiring 40 person-months of effort. This volume of work demands a budget of 1.2 crore rupees to support 8 full-time developers. If that initial baseline estimate of 80,000 lines is wrong, the timeline fails, the effort calculation breaks, and the budget becomes insufficient. Inaccurate size estimation structurally guarantees the failure of every downstream logistical decision. Because physical storage is irrelevant, engineers must identify the technical variables that actually increase a project size. Feature count is the most direct factor. An application limited to basic arithmetic requires a fraction of the architecture needed for an e-commerce platform that manages shopping carts and inventory tracking. Algorithmic complexity also drives size. A bioelectric facial recognition scan provides the same result as a standard password field, but the machine learning requirements impacts the architectural scale. A database built for 100 internal employees will collapse under the traffic of 10 million global users. Finally, system integration expands the workload. Securely connecting to payment gateways and third-party APIs requires rigorous protocols and intensive security checks. While two apps may look identical to the user, the back-end requirements can result in vastly different software sizes. When project managers underestimate that back-end complexity, the consequences hit the company's ledger immediately. Funding runs out mid-development, deadlines slip, and the engineering team is forced into heavy overwork, which degrades the final quality of the code. Overestimating the size of a project carries its own distinct penalty. Expecting a massive system when only a simple one is needed leads to bloated budgets, unnecessary hiring, and capital burned on excess infrastructure. Size estimation is a risk management mechanism that protects the financial health of the business and the developer's sanity. If measuring size is a mandatory first step, how do project engineers accurately quantify the dimensions of an entirely invisible digital product? The industry relies on 4 primary methodologies to assign a mathematical value to a project size. Function points, use case points, and object points measure the functional utility delivered to the end user, regardless of how the system is built. The absolute oldest and most common method in the industry measures the software construction materials directly, lines of code, or LOC. While LOC is the historical baseline for estimation, using code as a unit of measurement introduces a variable into project planning. Consider 2 developers building the exact same internal login system using 2 different languages. The first developer uses Java. Because of its verbose syntax, the login module takes 500 lines of code. The second uses Python. Its concise syntax achieves the exact same result in just 250 lines. The final line counts display a massive discrepancy. If a manager relies strictly on lines of code to measure size, the Java project appears twice as complex and twice as expensive to build. The difference in line count reflects the language syntax rather than the actual scope of the feature. This specific language bias makes raw code counting unpredictable. To make lines of code a viable metric, engineers run those numbers through specific mathematical models, formulas we will examine in Part 4.